Right? Let me do it this way.
I have no clue what to think anymore.
Did I have this right? L. That's good. That's good. Without the R there yet. I need the component. So I'll write the component as, how about cos theta? Where theta is I want that and so it's going to be Z. That's for that bit. This
Now it's getting weird. Watching the ball. This is interesting.
yeah, so this is capital R over you got it right?
I assumed that was just what I was thinking. In the book. Not everyone watching might have the book. One of my friends wanted to take this course, but he didn't have the schedule. So, and he's graduating. So this gives him a chance to watch Dr. Here.
Sorry, guys. I don't like to waste your time this way. And this is trivial. But doing it in front of you is messing me up.
The cosine theta you had there is what he has. And then,
Yeah.
then he integrates
I'm just
it.
checking the angle that I want. I want so
His, his cosine.
this is the theta. In that cosine theta. And does that give me, as theta goes to 90 degrees, that goes, yes.
But his theta is that of the z hat, so it's the theta coming from the b vectors that you now canceled. Or that you now canceled. That's where the
So
theta.
that's theta. Yeah,
That's why you have a z hat.
right.
That cosine theta.
So that's good.
Is z hat.
All right, so that's theta, cosine, but wait a minute. Yeah, cosine theta, that's good. All right. And cosine theta is adjacent over hypotenuse. And so that'll be R over that length there, and that makes this 3/2. Right?
It's what he, yeah.
Okay, that's what I like. That's what I'm going with. And then I do the integral in dl, and I get 2 pi r, r squared there now. And let's see,
That's it.
as z grows, the field drops off as z cubed. Yes, this is a dipole. I think that's right.
It is.
Okay. That's not what I have in my notes. But I must have miscalculated it. And that's what's in Ohanian?
Yeah.
Well, then
Equation
good.
46.
You could all read that. All right. So this was a case where we actually used little Léon Savart to calculate from scratch what the magnetic field would be at a particular point. And you can tell, given that this was a really nice symmetric problem, that if I had to calculate the field over here, it would get messy really, really quickly. There is a way to calculate the field over there that's not quite as messy, and I'm not going to do it today. Right? We're going to do that at the next class. And that's actually to use the Laplacian solution for the what we call now the scalar potential. It'll be each of the components, x, y, and z, right, of A obeys that. So given this, and given some boundary conditions that we will talk about next class, we'll solve the vector potential in all space, and then we'll take the curl of the vector potential. We'll find the vector potential in all space, and then take the curl of the vector potential in order to find the magnetic field in all space. And that will be somewhat easier than actually, that'll give us a closed form solution actually. Where here, we're basically stuck with numerical solutions. We can write it out, we can write the integral out, but it's going to be messy.
5 minutes.
Oh. Okay, so now I've got the field, I hope right, from a single loop of wire. So I had a long wire there, and over here I have a loop from a single loop of wire, which was 2I over C times 2 pi r squared plus z squared to the 3/2.
Where did you get the extra 2 from?
That I'm not so sure about. There is no 2 here. It's because I looked over there and somehow saw 2 that wasn't there.
You saw the 2 from the 2 pi twice.
That must be it.
That's what you might have seen in 2 pi,
Okay,
2i.
so this is the magnetic field of the loop on the axis of the loop. Now we can use this to calculate the magnetic field in a solenoid. So that gets modified in that if I've got this really long solenoid here, I sit at some point inside the solenoid, and I want to calculate the magnetic field from this loop here. Let's say this loop here, now that's my z-axis, right, is at position z prime, and that loop gives me a field at position z, all right? This thing only gets modified by switching. So if now the point that I'm measuring at is I'm not setting this point equal to 0. I'm setting, I need to know the distance here. So instead of z in there, I have z minus z prime. Okay? So this goes, when I want to put the loop anywhere, to 2 pi I r squared over c times 1 over r squared plus z minus z prime squared to the 3/2. Okay? That would be to calculate the field here due to some, the field at point z due to a coil at position z prime. And all of this is, we can really only do it on axis, right? So for the length of the solenoid, what we're going to have to do is integrate, so Bz for a solenoid, is I'm going to integrate that solenoid from end to end. Let's integrate it, for example, from position minus L over 2 to L over 2. 2 pi I r squared over c. Now, over here, what I'm actually going to do is sum up over all of the coils. each coil, the location of each coil. So the integral here actually would be, let's say, dn, actually it would be a sum over all of the coils. But I'm going to say the coils are densely packed, and that what I can do, looking over here, is that I've just got some coils in this region here. So I've got a number, some number of coils there. The number of coils there is going to be equal to the number density of coils, how many coils per unit length, turns per unit length, times dz prime, the little length there, right? So now summing up over all the coils, I have n dz prime. N is the number of turns per unit length over r squared plus z minus z prime squared to the 3 halves. That's the whole thing, right? Which we can go ahead and do the integral, but I won't. Exercise to the for the student. Actually, I'll do the integral. R squared plus but I'm not going to bother with writing down the limits. Plus and minus